Okay, guys, so let's talk about Virtual Lab 7, which is our synthesis of calcium carbonate. I am in here and I am in this experiment. And our first page, where we talk about the introduction of this particular experiment. Where'd it go? Oh, there we go. We've got our key concepts. This is a stoichiometry lab. And so we're talking about how we talk about the production of this material and how we go about doing the stoichiometry for this material. So we've got a couple of things that we talk about, which is how we break down the sodium carbonate to make sodium ions and carbonate ions. We talk about how we break down calcium chloride to make calcium and chloride ions. And then we take the calcium and the carbonate to make calcium carbonate. We can talk about the dilution of solutions, which is moles of solute is equal to the volume of the solution times the molarity of that solution. Okay, and the mass is equal to the moles times the molar mass. Okay, we can talk about the filtration of that material. So we can take and do filtration where we suck off all the liquid from it by pulling that out, and that leaves that solid on top of this filter that's here. And that's how this is done in the laboratory, is to do that. Okay. So we're gonna go through a bunch of questions and a bunch of different calculations. Excuse me, sorry, for how we do this. So the first thing we're going to talk about is we're going to be mixing aqueous solutions of sodium carbonate and calcium chloride to produce solid calcium carbonate. Okay, so we're going to be making this solid CaCO3. We want to order the steps required to predict the volume of 0.2 molar calcium chloride needed to produce 2 grams of calcium carbonate. So we want to make 2 grams of this calcium carbonate. This is an excess of sodium carbonate. So we have an excess of Na2CO3. Now, I'm going to tell you how I set this up, and this is what I always do in the lecture when I'm doing this. So I'm going to pull this off to the side, and then I'm going to pull up my remarkable. Close this because I haven't shared in a minute, so it doesn't remember what I'm doing. So I'm going to screen share again. And when I do this, I always set this up in exactly the same way. I like to have a system for how I do this so that I know exactly what I'm doing. So I write my balanced equation first. So I've got my Na2CO3, which is aqueous. I add that CaCl2, which is aqueous, to it. That's from the balanced equation that's on the right-hand side of the screen. I then get 2NaCl, which is aqueous, plus that CaCO3, which is a solid. Now, I know that this is a double displacement reaction. And so what that means is that when I mix these two aqueous components together, I get the Na from this first guy going with the Cl from the second, and this Ca from the second component going with the CO3 from the first. Okay, I know that's how this works. It's always the cation from one going with the anion from the other, and the anion from one going with the cation from the other. Okay, so I know that's how that works. And I know that I have to look at my two products to see how they're going to interact to see if who's going to be solid and who's going to not be solid. For my solubility rules, excuse me, I can look to see who's going to be soluble and who's not. When we look at our solubility rules from the data that we have, actually not going to show me that here, but when we have solubility rules that we can look at, what the solubility rules can tell me is that all of my group 1 metals, those metals that are in group 1 on the periodic table, and I'm going to pull up a periodic table for you. This is from the Royal Society of Chemistry. So this is what I like to use. So these group 1 metals, these guys, are always soluble. Okay. So if it's got one of those guys on it, it's going to be soluble. So this Na, this guy is going to be soluble. So that's why this is aqueous. And it turns out that the majority of the chlorides, chlorines, bromines, iodides are soluble as well. There are some exceptions to that. Silver is one of them. Lead 2, Pb2 plus is going to be one of them, and Hg2 2 plus. So mercury 1 is going to be one of the exceptions to that. But that's not the situation that we're dealing with here. So that's why this is an aqueous component. Okay. When we take our Ca2 plus, and I know it's a 2 plus because there's two Cl's minuses associated with it, and there's only two of them because Ca is 2 plus, then my Ca2 plus goes with the CO3 2 minus, and that comes over here, and what I see is that that is a solid. And the reason that it's a solid is because the CO3 2 minus tends to be insoluble, and there's not one of those group 1 metals on it, so it is an insoluble component. Okay, so that's why that one is an insoluble. Okay, so my solubility rules would tell me that. My solubility table would also tell me that as well. So if we had that available to us, we would be able to see that. But I know that's why this one is the way that it is. But they've already told me that, so I don't have to worry about it. Okay, but I know that's why that's true. Okay, so I'm going to go ahead and close that out so I don't have to look at it. So I know that this is the balanced equation that I'm looking at. I also know that I want to make 2.00 grams of this solid, and I want to know how much of this 0.200 molar, 0.200 molar, how much of that in milliliters do I need? Okay, so, and I have an excess of this. And what that means is that I have as much of that as I need available. Okay, so that's not my limiting reagent. Okay, I have as much as I need available, and so that means I can use as much as I could possibly need to do this. And so I just want to know, based on that amount of 2 grams, how much I'm going to require to be able to do this. So I need to know how to make 2 grams of this. So I need to start with that 2.00 grams of the CaCO3. Okay, and so if I want to make that CaCO3, I need to convert that from grams to moles. And I do that by dividing by the molecular weight. Now, the molecular weight of the CaCO3 is going to be found by adding the mass of the Ca to the mass of the carbon plus 3 times the mass of the oxygen. Okay. Now, do I know exactly what that is? Well, Alex is picky about what masses we use, so I'm not exactly sure what they're going to want me to use, but I can get an estimate. So I'm going to look at what my estimate would be based on this periodic table. And so if I look in here at my calcium, that's 40.078 on here. So Ca is 40.078. My carbon and my oxygen. The carbon is over here, and he is 12.011. And oxygen that's over here is 15.999. Now I know Alex is picky about the weights that are used and that there are other values that they pull up for that. But I only want an approximate value at this point just so I know what steps I need to go through. So I'm going to pull up my calculator, get an approximate value for that. And so I have my 40.078 plus 3 times the 15.999 plus 12.011. And I see that's 100.086. Now, I'm also going to look, because I think they said something. I'm still here. It says the molar mass of calcium carbonate is 100.09. Okay. So 100.09 grams of CaCO3 in 1 mole of CaCO3. So that takes care of the grams of CaCO3 and leaves me in moles of CaCO3. So I've done the conversion from grams to moles. I also know that based on my balanced equation, looking at the balancing that I have 1 mole of CaCO3 and 1 mole of Na2CO3. Okay, so for every mole of Na2CO3 that I use, I make 1 mole of CaCO3. So I can cancel out the moles of CaCO3, and I see how many moles of Na2CO3 are required. Okay, so that'll tell me how many moles of Na2CO3 are required. But I don't actually want information about that Na2CO3, do I? Nope. I made a mistake. So I want to know how many moles of CaCl2 I need. So I need to change this. The CaCl2. And it's still 1 to 1, so it's okay. CaCl2. Okay. So I just changed that to CaCl2. And that'll tell me how many moles of CaCl2 are required. And here's where things get funky. Right? I know that I have 0.200 moles CaCl2 in 1 liter CaCl2 based on the molarity that I have, right? So if I did that calculation, that would tell me how many liters of CaCl2 were needed. But I also know that if I take that answer from there, that would give me liters of CaCl2. And then I can take that and multiply by 1,000 milliliters per liter, and that'll tell me how many milliliters of CaCl2 I would need. Okay, so I can set that math up if I wanted to do so, and that would tell me. And that's the calculation that they want me to do here. Now here they want me to say, what are the steps that are involved? So the first step was convert the mass of calcium carbonate to moles. That's the first thing I did. Second thing I did was I compare moles of calcium carbonate to moles of calcium chloride. Then I look at the volume of, convert the volume of calcium chloride, compute the volume of the solution required, and then I convert the volume from liters to milliliters. So those are the steps that I took. And I know that because I wrote all that out so I can see what those steps were. Okay. That's part of why I do what I do. Now, to calculate that volume in using those numbers, I set all that up. And so now I can run through that math. And so I can pull up my calculator again. And I can say 2.00 divided by the 100.09 divided by 0.200 times 1,000. And that tells me 99.9. Now, looking at the number of sig figs, I have 3 sig figs in this initial number here and 3 sig figs there. So 99.9 should be the answer that I'm looking for. So that means that this number right here should be 0.0999 when we talk about the liters. So 99.9. And that's what I came up with. And hooray, it likes that. So I love it when that happens. All right. Now, I calculated the approximate volume. Complete the following steps. Use the clean graduated cylinder to transfer approximately 100 mils of that solution to the clean beaker. So here's my calcium carbonate. And I want to transfer approximately 100 mils of this material. So I put that there, put that back down. See, 100 mils. I did it in the wrong order. Oh well. But now I can put that one in there. And I'm going to zoom in. And this is 95, 96, 97. 97. 97.00. And the molarity of this one is 0.20. Molarity of this one is 0.20. We're going to mix those two together and dump that. And I see that we've got a cloudy precipitate. And so I want to note that. Cloudy solution due to information. I'm going to put this on top of the hot plate. I'm going to heat it for 4 minutes, although that flies by, and record my observations. It still looks like I have solid in there. Too many decimal places. And there's more solid. It looks cloudy-er after we heat it. Okay. Now we want to stir it. So one of these, we'll stir that up. We'll put that in there. And we're going to put that on the bench to cool it for 10 minutes. And then we go to the next phase. Hooray! And we're going to tear our balance. Use the forceps. Place the filter paper on the balance. .27. 0.27. And I'm going to take this and put it in the Buchner funnel. This down. I'm going to turn this on. We're going to wet it to make sure it doesn't go flying. Hooray. And now we're going to pour this mixture out. And now I want to rinse it with the DI water. And we're going to try and get all that stuff back in there. We're going to put that in there. and rinse it again. And turn off the vacuum. Take that out. Put it on the washcloth. And put it in the oven. Turn on the oven, let it heat for 10 minutes. Take it out, let it cool on the bench. And weigh the filter paper. 6.16. Four point 13. Did they clean their room?
I think so, and I told them that I expected them to not antagonize me showing effort.
Okay, so this is the information that gives us about how to calculate a percent yield. And we don't really talk about calculations of percent yield in the lecture. But this is the information that we get about how to do it, and this is something that we particularly look at in the laboratory. So what we have, and I'll minimize this, bear with me just a moment, is a discussion of how we calculate percent yield. So we need to look at the volume of the Na2CO3, which is smaller than, well, for us, the volume of the Na2CO3 was smaller than the volume of the CaCl2. Okay, it was smaller. And so that's going to be our limiting reagent because it's 1-to-1 ratio. Okay, and they're the same concentration. But we're going to have to set up this calculation for both of them because it's not always that easy to determine which one is our limiting reagent. Okay. So we're going to take that volume, we're going to convert that volume to liters, we're going to multiply it by the molarity to determine the number of moles of CaCO3 that are produced. The limiting reagent will be the one that produces the least number of moles of product. Once we determine the number of moles of product that are produced, then we multiply that by the molecular weight to determine the mass of product that is produced. Once we've determined the theoretical yield, because that's what we call this, is the theoretical yield of our product, then we'll look at the actual yield, the mass that we actually produced, divide that by the theoretical yield, which is the mass that we calculated we should produce, and then multiply that by 100. That will determine our percent yield. Okay, so that's what we're going to be looking at for this. So I'm going to take a screenshot of the rest of this so that we make sure we have the entire thing. So that's what we're looking for, is how do we calculate that entire thing. So we're going to go through the math to figure out, based on the numbers that we started with, how much should we make? And then compare that to what we actually did make, because we never make as much as we think we're going to make. As much as we would love to, that's never what happens. And so we need to make a comparison of how much we actually made comparative to what we theoretically should have been able to make. So that's what we're going to be doing here. So looking at the numbers that we actually have for this, we need to set up two calculations, one based on the 97 milliliters and one based on the 100 milliliters, both of them being 0.2 molar. So I'm going to take a screenshot of the amounts that we have here so I can take this over and do some math with it. I'm going to put this data in here, and then I'm going to open an Excel spreadsheet because that makes my life a lot easier. I have one open for something else, so I'm going to open a new one. And see if it'll let me. Oh, maybe not. Okay. So the way that I set this up is the milliliters of our material, the molarity of that material. So here, when we look at how much of that material did we have, yeah, 97.0 milliliters, that first material. I'm going to add another column right here so that we can then do the liters of that material equals that divided by 1,000. The molarity is 0.2 for both of them. Then I know the number of moles of our starting material is equal to that times that. So the volume times the molarity should give me the number that I'm looking for in terms of the number of moles of our product. And based on our stoichiometry, because it's a one-to-one relationship, it's going to be the same number. And that's, again, only because it's a one-to-one relationship between our starting material and our ending material. Okay? So we have a one-to-one relationship between them, and therefore we have the same number of moles of product as we do reactant. And then in order to get from moles of our product to the number of grams of our product, we have to multiply by the molecular weight of our product. So I need to know what the molecular weight of CaCl2 is. And again, looking at our it's not CaCl2, CaCl3, and they told us what the molecular weight of that material was. It's 100.09. And so I go this number of moles here times the molecular weight, and that tells me the mass that I need. So that's the mass that I should be able to make, and that's in grams. Now, based on the number that I started with here, these numbers, this one's 3 sig figs, this one's 4, okay? This right here is 2 sig figs, so I should be looking at 2 sig figs for both of these. So what I'm going to do is I'm going to reduce this to 2 sig figs. So 2 sig figs on both of those, 1.9 and 2.0. Okay. So that's the number of sig figs that I should have. Now it's still got that whole number stored in there. It's just only showing me those two. So this is my actual mass, or my theoretical actual mass produced. We're going to get from this data that we had, and this is the mass that we produced, was the 1.84. Now the lower of these two numbers was the 1.9, so that's my theoretical yield because it's the lower of those two. So we should be comparing the 1.84 to the 1.9, okay? And so we should be looking at 1.84 divided by the 1.9. And then, of course, we're going to be looking at that number as a percentage. And so when we go back into our actual lab, and we'll see if it's complaining about anything. Evaluate your calculations. 1.84 divided by 1.9 times 100. Which to 2 sig figs should be 95. Unless they want this reported as, it says to reevaluate the calculation. Yes, I'm here. I'm not sure why it's complaining. Percent. Well, it's not letting me put the percent there. Yeah. Okay. It didn't like the rounded numbers. Okay, fine. It's bizarre, but okay. I'll take it. I don't always agree with Alex and their assessment of numbers, but I I guess I understand why they're coming from. Print this. That's not what I wanted to do. Put that in here. Maybe it's gonna print. Anyway, I will print those and then I will be done. All right, I will talk to you guys later. I hope that that was helpful to you, and like I said, I will be available for any questions if you have them. Thanks, guys. Talk to you soon.